Okay, thank you for joining us today at 5 Things You Should Know About Resilience at Scale. Andy Jassy, when he was CEO of AWS, was fond of saying there is no compression algorithm for operational experience. And we firmly believe that. But with the 3 decades of experience collectively that the 3 of us have in operating AWS, we'd like to share with you 5 things that we and the broader AWS have learned about systems that behave a bit differently at scale than they do when they're earlier in their life cycle. And we hope that you'll be able to take these learnings back and apply them to your own applications so that you can learn some of the lessons we did the easy way and not the potentially hard way. I'm Alec Peterson. I'm the Vice President of Network Platform at AWS. I own Route 53 and Direct Connect, and I talk a lot with customers and AWS service teams about resilience. Mike?
I'm Mike Furr. I'm a senior principal engineer. I've worked on a number of services over the years. I've been here about 14 years. I now focus on EC2's availability.
Becky?
And I'm Becky Weiss. I'm a distinguished engineer at AWS. I've worked at AWS for about 10 years. I've also been a customer of AWS. I currently work in the area of IAM and identity and how it relates to data. In the past, I've worked with Mike on EC2. I've worked with Alec on DNS. And these are some of the non-obvious lessons that we have all learned operating these services.
Okay. And with that, I'm going to take the baton and talk to you about something that I am extremely passionate about, which is dependencies and modes. Now, I just want to do a quick level set on these so we're all speaking the same language of what I'm talking about when we talk about a dependency and a mode. So a dependency is something that an application uses to provide a function. Less abstractly, it can be an AWS service like S3 or SQS. It could be an internal service that your application uses, such as an authentication service of some sort. It could also be a foundational component of your infrastructure, such as the network or the DNS. Dependencies are not a problem. They are a cornerstone of service-oriented architecture. Without them, we'd just all be building monoliths. So we're very happy that we have them. But where dependencies meet one another are very interesting potential opportunities for failures. So we like to pay attention to where those meet and think about how they interact when the sun is shining, as well as when things are perhaps not going according to plan. When we talk about a mode, we are talking about a fundamental step function change in how an application behaves. So I'm going to give you an abstract example, and then we're going to talk about a very specific one that affected one of our services several years ago. For this abstract example, let's consider an e-commerce application that has a front-end fleet. So this is the fleet, a fleet. And it has a backing store for all of its data. A common component of an e-commerce application could be, say, a product catalog. A product catalog tends to be pretty static relative to the rest of the application, but it has a very read-heavy workload. So early on in an e-commerce site's life, one might say, hey, I'm going to put a cache in front of the database to take some load off of the database. Great pattern, takes load off of the database, reduces cost, improves customer performance. That's great. But a cache introduces the potential for a mode. Consider a bulk invalidation. Either an operator fat fingers a mass invalidation, the cache restarts. It can happen. If that happens, all of the traffic that was being fronted by the cache goes back to the database. Now, in a world where you had recently installed that cache, the database is likely scaled to handle that workload because it was handling it before the cache was put in. Probably not much of a problem. But if you consider the fleet growing as the e-commerce site continues to grow, the fleet scales horizontally, the cache scales as well. But the database does not have that same scaling signal because the traffic against the cache is protecting that database. So now, potentially many years later, you have much more load hitting the cache. So if that same invalidation event happens, you have much more load hitting that database, which could cause the database to have a bad time. This is one of the ways that modes can affect an application at scale differently than they affect an application earlier on in its life cycle. So enough with the abstract example. Here's a real one. As I mentioned, one of the services I own is Route 53. When we launched Route 53 many years ago, here's a very simplified version of how the Route 53 API worked. You have the API control plane. That's the equivalent of the fleet in the earlier example. It's handling the requests from customers to do things like add DNS requests and so forth, putting them into a database. And then we had a fleet of DNS servers, a handful of them at the time when it was still a smaller service, deployed around the internet that would periodically say to the database, what's new? I last got the information at time T. What's the amount of the changes that have come through since then? Easy enough, right? But as Route 53 started to grow, we found the database was getting a bit loaded with having to answer these questions. We realized, similar to the e-commerce product catalog example, all the DNS servers are asking the same question. There's no reason for the database to recalculate what has changed every single time. Instead, the database can simply periodically publish what's changed recently, and then the DNS servers can just ask S3. This makes the right use of the database in terms of doing the complex logic to figure out what's changed recently. It also is a very good usage pattern for S3. S3 is really good at just having somebody ask for an object and send it out. Everybody's happy. Now, over the years, as with our previous example, Route 53 continues to grow. The number of DNS servers continues to grow. S3 continues to grow. But what's not growing in here? The database. Yes, it is scaling, but it's not scaling with any attention being paid to how often the DNS servers are asking that question because it's not being asked that question. So this is the world that we were in on the fateful day when the database fell behind on publishing the changes to S3. It's not important why this happened. It just happens. It's the kind of thing we should have foreseen. And what happened then was the DNS servers noticed, gosh, S3 doesn't have the most up-to-date data anymore. But you know who does, who I was able to ask all those years ago, who has the most up-to-date information?
Oh, I know.
Who?
The database.
That's right, Mike. And sure enough, you have all these big arrows of load going and hitting the database in a modal shift. Now, if you're the poor operator who gets paged to figure out why, because obviously our operator was engaged when the database was falling behind, now you have two problems to deal with. You've got the original issue, but now the database is being hammered by all these yo-yos out in the DNS land saying what changed. I don't know, I'm figuring it out. So in addition to having to fix the initial problem, they also have to figure out how to tell the DNS servers, cool your jets, let it all get fixed and move on. This is clearly a modal behavior and was not the right behavior. So what is the solution? So consider the same situation. Publishing slows down. The DNS servers say, "Hey, I can't see any recent changes." Raise your hand. Say, "I need an operator to go and figure out what's going on." Do not change. Keep asking S3. Don't go faster. Don't hammer S3 harder. But continue asking S3, and then let somebody come in and figure out what's going on.
But isn't everybody getting stale DNS answers while this is happening?
They are, and that's a feature. Because our change propagation system is actually intentionally disconnected from the system that is serving up the data, right? And yes, we always want to have the most up-to-date data, but an answer that might be a few minutes old is way better than not answering that at all. So that is actually one of the success stories from this example. Whereas every DNS query was answered. Yes, the changes took a little longer to go out, and we have to fix that problem, but the core function of Route 53 was still working correctly. So the operator then fixes the issue. The DNS servers, once they keep asking S3, eventually they have the latest data. They say, okay, great, never mind, I'm going to keep on going. Everybody can move on. So this is a pattern that we've seen again and again at our systems that have grown over a long period of time at AWS. And the irony of this situation is the reason we had the fallback path was to improve resilience. In the short run, it likely did. As we were transitioning to this new system, working the kinks out, it allowed the system to recover. But in the long run, it actually harmed our resilience. So if there is a fallback, a modal behavior in a system, best to just either try to remove it or, even better, exercise it often. There are some of the most resilient systems that we have at AWS actually do have shifts in behavior. But they do that shifting so often that it's just part of their normal operation, so they get really good at it. And other lesson here is that if you are not going to fall back, it really motivates you to make your primary path as resilient as possible. Because if you know you're not going to fall back and you're going to just have to live with the situation until it can be resolved, it is further motivation to make the primary system as resilient as possible. So there are some other examples of modal behavior, not just these sorts of shifts. Other ones that are worth calling out, hard limits. Think about 32-bit integer rollovers, throttle limits, things of that nature. Understanding how your system behaves in those sorts of situations. Ideally, it does less work. It doesn't just keep on asking and hammering a system and doing more work. Thinking about what would happen if a part of your system encounters that sort of behavior will really help you be more resilient when you get into unknown territory. And that's modes. Mike?
All righty. So I want to talk to you about blast radius. So blast radius is a term of art. We use it a lot internally. You may have heard it through a different term, like scope of impact, things like this. But to me, what blast radius means is how much of a mess can you make from one change or from one component in your system. But blast radius is also a mentality. So usually when we design systems, we're thinking about availability. How many nines can I design my system for? Well, one of the things we've learned at AWS is that to build resilient systems, we actually need to think a little bit differently. We need to assume that things are going to fail and then be prepared for when they do. And this mentality is somewhat pervasive in our entire software development lifecycle. We apply it when we're designing systems, when we're implementing them, when we're deploying them, and when we're operating them. So to demonstrate how we apply this lesson at AWS, I'm going to use a simple application. I've got a few different EC2 instances here, and they're all talking to an Amazon S3 bucket. Since they're using the Amazon S3 API, they need an IAM policy to grant them permission to do so. So there's an IAM policy in this picture that's attached to the role for each of these EC2 instances. Now, we've probably tested this architecture. We know it works. Maybe it's deployed to production and it's working great. And it probably has a fair number of nines as well. It's going to be pretty available. It's pretty simple. But putting on my resiliency hat, let's think about what can go wrong here. And even though it's simple, there's a bunch of things that actually can go wrong. But the one I'm going to focus on is that IAM policy. So let's think about what would happen if tomorrow Alec updated that IAM policy and removed.
Alec, we'll talk after the session about how to do IAM. Yeah.
That'd be helpful.
Yeah.
Don't let suits write your code. So Alec updated this policy. He revoked our permission. And what would our availability look like? Well, it would look probably like this, which is not a very good day.
Alec's writing a COE. That's what Alec's doing.
That's a correction of error. This is a post-mortem that we...
Yes.
Right.
So this availability is pretty terrible. And if you look real close on this slide, you're not going to find any nines on it, despite our effort to build a system that has a lot of nines of availability. So when something like this happens, it's helpful to kind of walk through the series of events that triggered it. So in this case, Alec pushed his change. That caused the impact, right? We had some kind of alarms fire. Hopefully these are automated. And what we really want is for our alarms to be tied into our deployment system. So the deployment system can then roll back Alec's change, at which point, it takes a minute or two, but that'll take effect, and we'll have recovery. Now, this is a pretty bad outage. And we'd want to ask a bunch of questions about how did we get here? And just as Alec was alluding to, we actually have a pretty strong post-mortem culture within AWS. And anytime we have an external event, an internal service that has a problem, or even a near miss, we really try to dive in and understand what the process miss was so that we can make sure it doesn't happen again. So in this case, we might ask questions such as, well, why were customers impacted? We always like to start with the customer. Why was a bad policy was deployed? Why did we not catch this in pre-production? That's a great question. How can we make sure this never happens again? These are all really great questions, and we're going to spend a bunch of time on these questions and not stop asking them until we're satisfied with the answers. But there's another question that we're going to ask in addition to these, which we think is super important for resiliency, and that is, when this happens again, how can we reduce the blast radius? So let's go back to our architecture diagram. So if we put on a resiliency hat, the problem that we had in this event was not that Alec pushed a bad change. It's not actually the problem. The problem is we pushed the same update to all the instances at the same time. And so they all went offline at the same moment. Oops, I think, oh yeah, I jumped ahead, sorry. Okay, so now let's think about what we can do to mitigate this. Well, one common approach to a lot of deployments is partial deployments, right? You probably all use this for your code deployments. You deploy to a small section of the fleet, and then you deploy to the rest of the fleet. So we're gonna take the same approach here. We're gonna introduce a new policy. We're gonna call it the canary policy, and we're just gonna attach it to one EC2 instance. And then we're gonna have a second policy, which we're gonna call the full fleet policy, and we're gonna attach that to all the rest of the instances. Now notice, this is more complicated than the picture I had at the beginning. We've now got two policies. The deployment story is a little bit more complicated. First, you have to deploy to the canary, then you have to copy it to the rest of the fleet. Those can get out of sync. It's more complicated. But there's a benefit here. So let's think about when this happens again. So next week, Becky's touching our policy, and she makes a change, and she deploys it, and it breaks the canary instance. And so we might have an availability graph that looks like this. Now, it has kind of the same general picture, right? We have a trigger, we have a detection, we have a rollback, and we have a recovery. But it's much, much better, right? Our availability is now measured in a number of nines, even though there's still actually no nines on this picture. So there's one really important thing to note about this graph, though, that I kind of completely glossed over. And that is, why did we roll back? Well, presumably we had an alarm threshold here, right?
Wait. Hang on a second. That, like, you're kind of cheating here, right? Like, you set this alarm threshold at exactly the point where you would have detected this outage, right?
It's true.
Like, you know, if that line had been lower anywhere else, we would have a different story here.
That's the advantage of not putting anything on the y-axis, so we can, change the
This is a common trick of ours. Is not, right. You'll notice not a lot of y-axis over in our graphs.
All right. So if our alarm threshold was down here and Becky pushed her change, well, what do you think is going to happen? Everything's fine, and then there go our nines. And so we still have a bad day. So what can we do about this? What really happened here? Let's go back to our diagram. So if you look at our diagram and think about what the availability of each EC2 instance in this system experienced, the canary instance had 0% availability, and all the rest had 100%, even though our overall availability was some number of nines, right? It's a function of the number of instances we have here. And what's particularly dangerous about this is that we might pick a good value today for that rollback threshold, but if we then scale our fleet, that value might change, right? And so the rollback threshold that works today might not work tomorrow. So another takeaway from this slide is that EC2 instance with the canary policy, it's experiencing a different mode of operation than the rest. It's living in its own little world. And I call that a fault boundary, right? That EC2 instance has its own fault boundary. And so when we're thinking about rollbacks, we want to make sure we are monitoring each individual fault boundary to detect this. So if we had an alarm just on the canary instance, and it looked like this, it would be much more resilient to picking a variety of alarm thresholds. We'd still want to spend some time on what the right alarm threshold is, but we're now much less susceptible to it if we had picked a threshold that focused on that one particular fault boundary. Now I want to offer just a quick word of caution, which is that you should alarm on the fault boundary, but you should also alarm on your adjacencies. Right? So imagine we had applied the other kind of change to the IAM policy that allowed the canary to write things that nothing else in the fleet could read. So it's important, we would want to roll that back immediately, and so it's important to monitor the rest of your fleet, even if you're just deploying to one particular fault boundary. And of course, you also want to disjunction in some other health monitors that you have for your application to tell you if it's working correctly.
Okay, now, but what if you really actually have to make a high blast radius change? Like there's situations where I think this is unavoidable.
I make Alec do it.
Okay.
No, so it's a good question.
VP approval.
There are times when we have no choice, right? I think a lot of changes with enough time and effort can be made low risk, but there's definitely a category of changes out there for whatever reason we need to get out. So what can we do in those cases? Well, let's think about it. If I'm about to deploy a change, one thing I can do is apply a strategy of roll back first and ask questions later. So I've just deployed this change. I know it's high risk. I tested it, but geez, I'm not really sure. So what I'm going to do, maybe seconds after it goes into effect, is roll it back right now. I don't even know if it's going to work. I'm going to roll back now. Turns out it didn't work. Oops. But the good news is, because I knew it was high risk, I also made sure that rollback story was really fast, that rollback path. And so now we get recovery very, very quickly. And by the way, our alarms might not have even fired yet, right? Our alarms might fire over here. And so we're proactively rolling this back immediately. We apply this technique in a few different areas, but really wherever we think it makes sense. So one example is changes to the core networking devices in the Amazon network. Another is when we're doing like data migrations or like changing the authority from one system to another. We might move it over and then move it right back. We should always have a solid rollback path, and we try to test it very, very aggressively. So this change didn't work. We rolled it back. What does this have to do with blast radius? We still hit 0% availability. Well, our blast radius decreased here in the dimension of time, right? Our event was much, much shorter. And that's a super important aspect of blast radius as well. How can you mitigate the issue faster? So we did this change. It didn't work. We're going to go do a postmortem. We're going to figure out what went wrong. And we're going to do it again. And we're going to keep doing it until we get a graph that looks like this. We roll it forward. We immediately roll it back. And then we check and make sure, did it work? And if we're confident it did, then we'll roll it forward one more time and just leave it be. So when thinking about your architectures, I hope you take away the message that you should always be thinking about when they will fail, not if. It's super important that you understand when you make a change how big of an impact that change can have. And if you're targeting a particular aspect of your system, make sure you're monitoring the exact results of that change and you don't average it out with other components of your system and lose insight into what the overall effect is. And then finally, for your largest risk changes, think through just what can you do if it goes wrong, and the answer might be make it shorter. And if you can make it only a few seconds of impact, it might be that nobody notices. Okay, so I want to elaborate a little bit more on that last point, which is that the duration of impact for blast radius. When we talk to customers and talk to them about availability events, either theirs or ours, one of the themes we hear is that the shorter the better. Which, obviously, like who would want a longer outage? But it's feedback we've taken to heart. And when we look back over our time at AWS, one of the correlations we see of events that have long times to recovery often have a queue hiding in their architecture somewhere. Now, queues are actually really great. I love queues. We use them all the time in our architectures. So this is not a slide to say that queues are bad. Actually, they're fantastic. And the reason they're fantastic is that they allow you to decouple the availability of systems, especially when you have a producer and a consumer that can be separated in that way. Queues are so popular, we have a service, the simple queue service. It's actually one of the oldest Amazon services. It's one of the first ones we built. We use it in a lot of different places. So just to review why this helps us with decoupling, so you have a producer, it offers some work onto the queue, and as soon as it's done that, the producer can respond back, okay, to its caller, its job is done. Then we have a consumer, that pulls the work off the queue and does whatever it needs to do with that work. Everything's great. And if service 2 here has a little hiccup to our consumer, service 1 has already acknowledged success, that it's in flight. Service 2 will eventually get to it. But what if service 2 doesn't eventually get to it? What if it's going slow? Let's think about a prolonged outage. So maybe service 2 got a bad deployment. Maybe there's a problem with the network. Maybe there's a problem with DNS. But for whatever reason, there's a problem with service 2. And so what does this look like to service 1? Well, service 1 just calls SQS, or whatever queue system you're using, and it adds messages and adds messages and adds messages. But of course, service 2 there, well, it's going a little slow. What does this mean for our availability? For service 1, the availability is great, right? It got success adding things to the queue. It can return success back to the client, whoever its caller is, its customer, and everything's great. But everything's not great, right? The reason everything's not great is this queue has a lot of items on it. So you probably see where I'm going with this. We're going to want to measure that queue, right, for resiliency. One way to measure is just the number of items in the queue. That's OK. The measure I prefer is actually the age of the items in the queue, because this is more tied to your customer experience. So think about like an average or some percentile of how old are the things sitting in the queue. And if you do that, if you have this metric, you can plot it an alarm on it, and then you can look at it, what happens when you have an availability event. So let's say we do have this event where service 2, the consumer, goes slow. Well, your outage graph is going to look like this. Initially, you can kind of tell when service 2 breaks there. It's where the queue starts to back up and fill up with items. And then obviously you can see where it recovers, which is when we have this recovery slope. There's a couple of really interesting things about this graph that I want to highlight. One is the slopes of the two lines. So the consumer recovery slope is much sharper than the impact slope. Imagine if that was not the case. If the consumer was slower to pull all the items off the queue, our recovery time of the entire event would be dominated just on draining the queue long after service 2 had recovered. This isn't just made up either. This is a graph that is slightly doctored of an internal monitoring system that we have, where we had a real system of pretty sizable scale where the consumer broke. And this is the age of items in the queue over time. Same exact shape. Well, there's a little bit of drama there on the right because it's a real world example, actually. The details of the drama doesn't matter, but this is exactly the shape that we see time and again. Okay, resiliency is about thinking about when things fail. So I've kind of made the point that you don't want your queue to grow, but if your queue is growing, what do you do? So if you're not familiar with the Amazon Builders Library, I'd highly recommend you take a look at a collection of articles there. But there's one in particular related to this topic on unbounded queues, written by a colleague of mine, David Janacek. He goes into a lot more depth than I do, so if you're interested in this topic, please do take a read of his article, and he goes through a whole bunch of different mitigations and ways to think about queues and using them successfully at scale. But for this talk, I want to just highlight two aspects of it. The first is a technique called sidelining. So let's go back to our example where our consumer is going slow. Remember, this was the case where the producer is adding an item, and it just builds and builds and builds, and eventually we have this picture, right? The moment the consumer recovers, what does it start doing? Well, the queue, in most cases, is a FIFO queue, first in, first out. So that means the things that are in the front of the queue are actually the oldest. And from our experience, a lot of times, the oldest items are the least interesting. The ones that appear to show recovery to customers are the ones that are arriving right now. And so for a lot of domains, it can be helpful to split these apart. So a technique you can use is to put a threshold and say, like, everything that's older than this threshold, we're just going to quick dump it on a side queue. Now, the consumer's job is to process the main queue and do all the work that's showing up right now. As a second, lower priority, it can process the backlog. Maybe we need to scale up to do that. Maybe it'll take a little bit of time, but all new requests are being processed successfully. There's a variant of this technique where instead of using a sideline queue, you just delete all the updates. Now, that's obviously going to depend a lot on your domain, if that's safe or not to do. But if you can delete all the stuff that's too old, it's what happens to your time to recovery. It dramatically shortens. So I want to share a little bit of story. I used to work on the VPC team at Amazon, and VPC is responsible for controlling things like security groups and route tables and things like that. And the architecture of the system looks somewhat like this. It's a little bit simplified. And this actually isn't atypical for a lot of AWS services, where you have a control plane at the top, and this is what is receiving the customer API calls. And then there's a data plane at the bottom that actually turns those intentions into reality. And in this service, we actually had a queue that the control plane would accept customer requests, put the updates on a queue. Those updates would then propagate down to the data plane and be applied. So let's think what would happen if we impaired that propagation service. If I can, oops, wrong button. There we go. Okay, so if the propagation service is impaired, I think you know the story. That queue is going to grow and grow and grow. Now, because this is the VPC updates from customers, if someone sends us 2 different updates to their security group, we're not at liberty to change the order of those, nor can we throw them away. So that sidelining technique I used previously doesn't apply here. So what can we do? Well, we use a different technique called back pressure, which is we're going to allow things to build up in the queue, but only up to a point. So this is just a bounded queue by a longer explanation. But what's different here is we actually tell the control plane what the depth of the queue is. And so when the control plane sees that the queue is full, what do? Well, we fail customer calls.
You're failing customer requests?
Yes.
I think you lost some nines there.
I think I lost more than one 9. So as long as this queue is full, we're going to continue to fail calls. This was actually controversial at the time when we did this for exactly this reason. And the reason why we did it was because it made our recovery times predictable and fast. The moment the provisioning or the propagation service recovered, we knew that we would be at full recovery very, very quick, and we wouldn't have this giant backlog that could last for minutes or hours. And so we're explicitly trading off availability for resiliency in this case. So I hope you all go back and look at your applications and think, where do I have queues? They don't always have queues in the name. So think about things like log files on disk, rows in a database, anything of that nature that can get backed up.
Like a buffer.
Like a buffer, yes, many things. And make sure you have a stat on how far behind you are. It's also critically important to know how fast you can drain that queue. If you don't know what that number is, a good technique is in your pre-production environment, turn off the consumer, fill up the queue, and turn it back on and measure how long it takes. And do that all the time. Did your deployments make it slower or faster? Always make sure you know what that recovery time metric is. And then finally, if all else fails, have a bounding strategy for your queue to make sure that you don't accumulate so much work that your recovery time is going to be lengthy. And with that, I'm going to hand it over to Becky.
All right, thanks, Mike. So this next topic is on errors. And errors this is actually one of my favorite topics here because the connection to availability and resilience and ability to recover quickly is very non-obvious, but very real. This is something that we've seen quite a few times. Okay, errors. You encounter errors every day unless you're perfect, which you're not, right? And actually errors, there's many varieties of errors that you can get whether you're calling an AWS service or calling a dependency of your own. And per the RFC, they're actually kind of in two important categories here. It's 400s, client errors, it's 500s, server errors. You've probably seen both of these. You've probably seen more of those client errors than the server errors. The client errors are, well, something was wrong with your request, right? You didn't have access to the thing. The thing you're asking for wasn't there. The combination of parameters that you gave is invalid. In fact, I would wager that it's definitely true for me. The first time I try onboarding onto any new service, AWS, something else, my first request always returns some kind of a 400, right? You see these all the time. 500s, on the other hand, you see these less, right? 500s means something server side, it's not your fault, something on the server side caused, maybe an unhandled exception, something like that, caused you to get this error. It's not anything that's actionable by you. You might come back later and it'll work. And of course, both of these, here in AWS, both of these types of errors very much exist in our world. In fact, I'm going to show you a graph of some graphs of one of our very large scale services. One of them is 400s and one of them is 500s. I'm going to give you a second here to try to figure out which is which. And of course, because most of you are probably very good test takers, I actually switched the graphs, right? And what you're looking at here on the left-hand side, you're looking at 500s. And on the right-hand side, you're looking at 400s. Now, how did I know that? Well, I know that because I made the graphs. But I also know that because of the shapes of the graphs. On the left-hand side, we have 500s. You can see this one's kind of bumping along at 0. And you might actually be wondering, I bet somebody here is wondering, well, why isn't it actually 0, right? If your service is doing well, like why isn't it actually 0? Well, like I told you, this is a very large scale service, lots and lots of hosts. When you're operating at scale, you're actually not going to get it 0, 0, 0 on this. This graph is very zoomed in. You'll see there's a little noise on the bottom. A host goes bad, and there's automation that takes it out of service, but there's a little bit of time until that automation kicks in. Now, the 400s is following that normal. You can see this is, you can probably guess this is a week worth of 400s. You see that kind of weekly diurnal pattern. 400s, well, we're getting 400s all the time, right? A customer is asking for a thing that isn't there. A customer doesn't, customer shall remain nameless, wrote their IAM policy wrong, is getting an access denied, right? And how do these look in your service? So Mike asked me when we were putting together this slide if this is source code from S3. It is not. But
You don't say what in S3? I'm shocked.
So what you're looking at here, but roughly, very roughly, if you have implemented a service, the code that returns a 400 error and the code that returns a 500 error, they will kind of look like this. The 400 errors are, well, everything's actually working fine from your services perspective. You have just, different cases, usually in some kind of if-else statement, right? If I didn't find it, return a 404. If the IAM evaluation, turned up access denied, return access denied. These are anticipated, known cases. So there's usually specific code to handle it. The 500s, well, 500s aren't always implemented this way, but often they are. You tried to get through something and some kind of exception got thrown in here. Maybe a dependency was broken, maybe a problem with the network, maybe DNS, right? But at the bottom, something happened. We are not going to succeed this request. It was not one of the cases that we're actively looking for, so we throw a 500. Of course, there's other things, kind of overload, brownout, those kinds of things that we may have deliberately thrown a 500. So the question is, why does this difference matter? I'm going to tell you that it's actually very, very important to availability and particularly ability to recover from an outage to get this code right, to get your 400 cases classified as 400s and returning 400s, and your 500 cases classified the right way too. So what does this have? This is obviously very nice for your customers if good ergonomics, right? Return good, useful, actionable error codes that tell them what happened and what to do next, but actually matters for availability. So let's say I doctored this 500s graphs to kind of make an outage. It's an outage with 500s. And you can very clearly see that there is a period of impact here. Things are failing. It is very clear that something's wrong in this picture. And I set an alarm threshold, I did a good job of that. My alarms are firing, maybe automated remediations are taking place, maybe something rolls back, maybe an operator gets engaged, whatever's supposed to happen when things are going poorly. This is clear and I can react to it. What about 400s? If it's raining, what if something's going wrong? What does my 400 graph look like? Well, doesn't look like much, right? This is actually not giving me very much information. This is actually why it's important to classify these things right, because one of them is a source of signal and the other is a source of noise. So you don't want to fold in some of your signal to your noise. You don't want to fold in some of your noise to your signal. So what is this graph telling us? It's actually not really telling us whether we're failing or succeeded. This is kind of what the graph's supposed to look like. And in fact, what can we do with this graph? Well, the 400 graph, it's not totally useless. It's actually pretty useful for a number of reasons. For one thing, like your success graphs, it has a shape. It has a shape that you're expecting. And features like CloudWatch anomaly detection will actually help you see when it's getting out of this band. So, let's doctor this. Let's say there's a period of time when our 400s, our service is returning 400s client errors, but it's outside the normal range. So what is this telling us? Well, the truth is I still don't know what this is telling us, right? There's actually two possible stories here. And actually, it's worth having this graph so that you can figure out which is which. Possibility one is that we've just deployed a change to our service where perhaps inadvertently something that was succeeding yesterday is 400ing today. Imagine you push a new configuration and some limit, some max value of some parameter, you accidentally made it lower. So somebody was within range yesterday and now they're out of range. That's actually, as the service owner, it's your problem. You got to do something about that. The other possibility is some customer got very enthusiastic with making wrong calls. right? Nothing's actually going wrong, but like a top talker is driving this picture. You actually don't know from this picture which is which, but this is an important graph to be looking at as well. It can't be alarmed on as easily as your 500s, but it's certainly telling you something. Okay, so why does this matter to resilience? Because it matters to time to detection. If you have the signal and the noise classified well and cleanly, you can get a better time to detection. And I'll tell you at AWS, both Alec and Mike have talked about this in different ways, but actually when we're doing retrospectives on operational events, outages, issues, the most important thing is how quickly got the issue to end, right? So that's, how quickly you can make the issue end is time to detection plus time to mitigation, knowing there's a problem and then solving mitigating the problem. And so time to detection is something we actually have a laser focus on. And so getting the most signal you can out of the kinds of errors that your service returns is actually really important to having shorter outages. I love this connection because it's so non-obvious. The 500 needs your attention. The 400 might need your attention. So let's go back to a 500s graph, and let's look at a service that took a really short period of impact. But clearly you can tell from this graph that there's a period in which something changed, something's going wrong. Let's say this is a 500s graph. So this is my availability graph. I have mostly it's at 100%, but there's this one point that isn't good. Now, of course, it's a tiny little issue, right? And I've got my graph, I've got my alarm threshold with my 9s here, and it looks like everything's good. My alarm isn't firing. And in fact, by the absolute numbers, I am doing quite well. Particularly, it's a 500, it's retryable, it's happening at a really low rate. Most of our customers are going to skate over this with retries and won't even notice it, right? The question is, whose 9 is that exactly? If we're talking about this service as one monolithic unit and this is a percentage of its availability, then actually I agree with the guy in the stock photo. Things are actually okay. There's something to look at, but things are okay. But a lot of the times that's not actually how your service works, particularly at a large-scale service. You might have something like a cellular architecture, some kind of sharded architecture, maybe where you direct different customers to different kind of instances, cells. There's a lot of benefits to this architecture. We use it all over the place at AWS, lets you run your service at a contained, known, anticipated scale. But if I think about this, then, and I'm just looking at a single availability metric, it's going to be the average of these four. And you saw from Mike's part of this talk, what happens when you average these out? You actually lose a little bit of fidelity on what's actually happening. If I were to graph each of these cells' availability separately, you notice that if you're a customer assigned to the blue cell, you are actually not doing as well as previously thought. Everybody else is getting close to 100% availability. You're getting something a little bit different. So that's why this is really important. That's why this is really important if you have any architecture like this, that you actually be measuring each separately. Because a single customer, their experience might be different from your experience if you're averaging the whole thing out. One more thing on this topic of errors that I actually wanted to mention, because this is, I would say that for those of us who operate services at AWS, CloudWatch Contributor Insights is probably our favorite feature of CloudWatch. We get so much insight, because if you think about the scale at which we run, the number of different customers that we have, each of them having their own individual experience and journey in the cloud.
Is CloudWatch Contributor Insights the kind of thing you could have looked at to see if those 400 errors were
a
yeah. Customer?
Yeah, for sure. I mean, and what you're looking at here is this is actually a screenshot from one of our services of the 400 errors being delivered at the service. Nothing's wrong at this service. It's just a typical example period of time. And, the nice thing about Cloud Contributor Insights is even if you have lots of different, your normal graphs can't support that level of dimensionality in the graphs. But Contributor Insights is designed to do exactly that. So it's showing me the top talkers getting 400s here, errors by account. Couple things we can notice about this. First of all, the blue customer and the orange customer, they are having a fundamentally different experience on your service than everybody else. Now, why is that so? It might be, we've seen all of these stories. It might be that the blue customer is actually deliberately running a test load that is deliberately running into errors, like they want errors and they're just running that at a very, very high rate. Or it could be that they have something misconfigured. And depending on the circumstances, it might be the kind of thing where you may even want to reach out to them and say, like, hey, what you're trying to do is not working, right? You need to do it this way instead. The green customer here, they're having some kind of pattern here, right? That's interesting to look at too. Again, it's probably true that everything is okay with this service, but there's something to learn about your customers and how they're actually using your stuff here. Okay, so I love this topic. Errors and how you have implemented your errors in your service and getting them right matters so much to your ability to detect the actual problems, the 500s, and react to them. Really important for these shorter outages. And then with those 400s, they are a source of useful information. I recommend taking a look at Contributor Insights if you've never looked at that. Source of information about how your customers are actually using your service. We use that all the time. Our final topic of our 5 topics beyond the 9s is retries. Retries are actually closely linked to this previous topic of errors. Because as we talked about before, you get a 500 error, you should retry. So, okay, retries, you've probably seen them. A retryable error, like a 500 error. So your client is making a request to a service that may be temporarily unavailable, unreachable, something like that. You get a 500. So, not happy about that, but it's a 500. 500 means not my problem, it's their problem, so let's try this again. So we do that again, still not working, and usually 3 is a number that appeals to a lot of people. It's got some nice symmetry. So we do a 3rd one, and that succeeds. Now, the truth is, when you are calling AWS services, you're probably using the AWS SDK and all of these programming languages that we support the AWS SDK. The nice thing about using the AWS SDK is actually a lot of work has gone into the retry behavior there. So you're getting that for free. You don't have to do anything or configure anything or figure out how long to wait before you retry. It's kind of doing this for you with good sort of back off and jitter kind of practices. You don't need to think about it that much. But if you're making calls between your own dependencies, thinking about getting this retry behavior, implementing good retry behavior is pretty important. Now, here's another thing about retries and running services at scale. So retries are happening when something bad is happening. The reason the retries are happening is because 500s are being returned from your service. And I'm showing you graphs of 2 different AWS services, each of which had some kind of brief impairment. So the green lower graphs for these 2 services are false, so the inverse of that availability graph, 500s being returned from the service. And I want you to notice, they're very different services, their patterns are very different. These 2 operational events are clearly shaped very different facts, but notice what's the same about these 2 stories, because this is always true. When your service is throwing faults, you will receive more load.
That sounds like a mode.
That is a little bit of a mode. You enter into retry mode, and it's pretty much unavoidable, right? When you have errors, you're going to be taking higher load, which, this is another one, now you have 2 problems kind of thing. Again, you can't really get out of this situation. This is just sort of a law of physics of returning 500s. But there are some things you can do to make this situation a little bit less challenging. Okay, so we're going to build a microservice architecture here. Service 1 calls service 2, calls service 3, calls service 4. And so that's a pretty clear dependency. Nothing wrong with that dependency. This looks like a great architecture. And so let's talk about what happens when, not if, but when service 4 is having some kind of availability event. It's throwing 500s. Okay, so service 3, we got all the way down to service 3 in our call chain. Service 3 called service 4, didn't work out, so service 3 does the right, kind of exponential backoff and jitter, makes a retry to service 4 like it's supposed to. Still not working. Let's try another retry. Still not working. So what does service 3 do? Service 3 says, no, 500, right? Like a server error. I can't. Service 2, I can't fulfill your request, and it's not you, it's me, right? Okay, so what does service 2 do? All right, service 2 is like, okay, service 3, let's try again. All right, this happens again. Service 4 is having a prolonged outage here. Of course, the longer this outage is, the more load for exactly this reason.
It can build up pretty quickly, though, can't it?
Yeah, because if you think about this, let's do a little bit of math here, right? Service 2 tries it again, service 1, what's the math here? You remember from high school algebra that what we are looking at here is a geometric sequence, right? Every time we go one service down this chain, we're actually getting exponentially more load. Now, this is a bit of a caricature of how these work, but these things actually do work this way, right? You have this amplification of retries along the way. And so what does that mean for service 4? Service 4, on its worst day, is getting maybe an unprecedented amount of load. And what do you think that's going to do to service 4's ability to recover quickly, even when the lights come back on? Now, what do you wish were happening here? Of course, we wish service 4 weren't having an outage, but again, we're here to talk resilience. We're not here to talk about being perfect, right? You actually kind of wish that it worked this way. You wish that service 2 and service 3 actually were aware of their intermediate status, weren't driving further retries, and we let service 1 drive further retries because we actually did want to complete this request. This one actually might do a little bit better because if we look at the picture on the left versus the picture on the right here, which one do you think is going to recover faster? Well, certainly the one that isn't taking huge amounts of load. Now, so I just said that maybe service 2 and service 3, maybe they shouldn't do those retries. But there's a little bit of a human factor.
Wait, I own service 3. Are you saying I'm going to have to...
Oh, you own service 3?
What do I have to do here?
Well, you like those 9s, don't you, Mike?
I do like those 9s.
Yeah, and if I told you that you shouldn't be retrying to service 4, what would happen to your 9s?
I would lose them.
You would lose your 9s, and Mike might be very sad about that, right? He might pride himself on those 9s, and he might lose a 9 if he doesn't get, because there's all kinds of situations where maybe service 4 takes these little hiccups, and his retry strategy is actually working like a champ, right? Like, it gets him, rather than having to, go back to service 2 and say, oh, I couldn't do your request, it actually, from Mike's perspective, from Mike's local perspective, this is worse, but from the global perspective of this service, we actually get a much faster recovery. So these are things to think about. Like, you might locally get lower availability, fewer 9s, and we're going sort of beyond the 9s here, thinking time to recovery actually more important than our 9s. All right. Now, one of the things that we actually think about quite a bit in these recovery scenarios under load, throttling, rate limiting, is really, really important. If you end up in this picture on the right, it's actually your best way out of this, to be able to throttle to speed the recovery. Now, of course, here you also are, you're also losing some 9s here because you're pushing customers away, but this might help you recover quite a bit faster. It might actually help their retry succeed faster. Now, this is all well and good. I painted retries as a little bit of a villain. Of course, that's not quite deserved because these good retry behavior does actually help you skate over issues. But the problem with retries is actually retries are a form of modes, as we talked about before. So what if you want retries, but you don't want the modal behavior? And this is actually, Alec and I have both over various points in time worked on the DNS infrastructure that serves customers' EC2 instances. This service today is called the Route 53 resolver. It's, if you know your virtual private cloud concepts, it's at the .2 IP address in your VPC. This is where your DNS by default where your DNS queries go to get resolved in EC2. And there's vast amount of infrastructure in EC2 to help make that work. Back then, we just called it EC2 DNS because Route 53 Resolver didn't have a name yet. But if you think about, well, DNS from an EC2 instance is pretty darn important, right? If DNS isn't working for a customer of EC2, pretty much from their perspective, they're not having a network today, right? So DNS needs to work, and so we ran these resolvers in the EC2 network that your DNS query would go to, and of course a pretty large fleet, which means at scale there's going to be some period of time when some host has gone bad and hasn't been taken out of service, and at that moment the DNS query to that host would fail. The customer is actually not able to resolve DNS, not able to do what this EC2 instance wanted to do. So okay, maybe we want to retry. Here's the problem with retry. There's a lot of EC2 instances in the availability zone all sending DNS queries all the time. And if there were some kind of impact to the resolver hosts, maybe a bad deployment, maybe something that affected multiple hosts simultaneously, you could definitely imagine a lot of scenarios where that could happen. Are we all of a sudden going to 2x the DNS traffic in the availability zone? Well, that's going to be a bit of surprise to, that's a mode. That's going to be a bit of a surprise to all of the infrastructure that we had there. So how do we get our cake and eat it too? Well, the best thing to do if something's failing is nothing, but we want retries. So what we're going to do is we have today, when you make a DNS query from an EC2 instance, you don't see any of this, but it actually goes to 2 DNS resolvers. Now, in the vast majority of the time, both of them come back with the right answer, and you get one of those answers. You get back whichever one came back first. But if one of them isn't coming back, or one of them is just being very slow, you get the other one. You don't even notice. Now, of course, this has a little bit of a trade-off because it means that we are processing twice the DNS requests all the time than are actually happening. This means we need twice the scale. Something like this, it's important enough. But this is a technique where when it is really important that you have retries, and you're willing to pay a little bit of scale to do that, you can consider just proactively having retries all the time. So this is an unusual case, but this approach has been extremely effective for us. All right, so that brings us to the end of retries. They sound bad, and they often do drive additional load when something's already going wrong. And so techniques to mitigate that, you're not going to eliminate it, techniques to mitigate that as much as possible are really, really helpful in getting to a quick recovery. And then, if you really do need retries, if retries are really, really important, but you don't want a modal shift in high scale, and you're able to pay for the additional, the additional capacity, one thing you could do is just retry all the time. All right, so those were 5 things. And my hope is that I bet a lot of you are experienced operators. A lot of our cloud customers have fantastic operational practices in the cloud. I hope even if you have a lot of experience, you came away from this learning something new, maybe looking at something in a way that you hadn't looked at it before. So we talked about dependencies and modes. We talked about how, the way to deal with a dependency is not to completely shift modes when it fails. We talked about blast radius. We talked about kind of figuring out how to segment it so that the changes that you make are limited in the scope of impact they can cause. We talked about queues, which is really kind of blast radius along a time dimension if you think about it, and how to limit the backlogs of those. We talked about errors and this kind of unexpected connection between time to detection and how well and cleanly implemented your code is. And then finally, retries. How to deal with the inevitable additional load that retries will cause. So thank you so much for joining us at this session. We had a lot of fun putting together what we wanted to share with you, and so really appreciate you sharing it with us.